Alright, welcome to lesson 2, and we're going to be talking about position time graphs. So this is our first type of graph that we looked at last year. The second one was velocity time graphs, so we'll go over that on a separate video. So position time graphs, where we've got position as our dependent variable and time as our independent variable, and the key here is what our slope is equal to. So if we think about slope as, our rise over the run, also our y2 minus y1 over x2 minus x1. Now that's general in terms of math. Now if we're looking at a specific position time graph, we can rewrite the y's and x's as d minus d naught, and those are position vectors, and then t minus t naught. Now that's again symbolizing our final minus initial, which allows us to rewrite it as delta d over time interval, which should be fairly familiar. That is displacement over time, and that is velocity. So the key here is that velocity is determined by the slope of a position time graph. Now there's some interesting points here that we need to be aware of. Now if we have a positive or negative slope, so depending on which one you have, it indicates the direction the object is moving. Now the third option here, so you have positive or negative slopes, or you could have a zero slope or a horizontal line, and that is an object at rest. So those are two options that we have to keep in mind. And one other key point that is good to keep in mind with graphs of a position time graph is that a steeper line, whether it's positive or negative, means that we are going faster. Alright, so now that we have those kind of ideas in our head, let's work on calculating slope of this position time graph. So here we are, we have a graph. We're calculating the velocity for each 5-second interval. So 0 to 5, 5 to 10, and 10 to 15. So take a second to do that, and I'm going to pause the video, do that, and check back in about 5 seconds. Alright, so welcome back. Let's take a look at the calculations that we did here. So for the first one, you notice I started with the equation, I plugged in our numbers, and I'm just pulling them straight off the graph here. So 50 meters and 0 meters, and then 5 seconds and 0 seconds. So I'm just pulling this information right from the graph, putting it in, and calculating it out. It is important that the direction is there, or else it's not a complete answer. One thing you'll notice, I gave it a V1 subscript just to indicate that, I'm leaving this as section 1, and then subsequently section 2 and section 3. Now you can do this, it's just a way of organizing your work by applying subscripts. For the second one, very similar situation, just pulling the numbers right from the graph, 20 meters north, 50 meters north, and then 10 seconds and 5 seconds. But you'll notice that results in a negative answer. The best way of writing this would be to avoid that negative and switch the direction so that we have 6 meters per second south. And the last one, I didn't even calculate it because I know that a zero slope or a horizontal line is an object at rest, so 0 meters per second velocity. So you don't have to calculate that because that's something that we are assuming to know. The second part of this example, calculate the speed and average velocity over the entire time. I want you to do that, and we will take that up in class. So let's move along and take a look at our next example. Now this example will require us to actually graph our data. So we have Q, James Bond character, performs an experiment on a stealth vehicle in his top secret laboratory. The data from his experiment is shown on the table on the right. Following all the steps, draw a graph of the data and then find the slope of that line of best fit. So first, let's just graph it. Pause the video, do that, and come back to see a final result of the complete graph, and then we'll go through the calculating the slope of the line of best fit together. Alright, so you can see here that we've got a completed graph with a title, a label on our dependent axis, and as well as our independent and dependent axes. And then, numbers, units, it's all there, and then we've plotted the points that were in our graph. Now when I plotted the points, I dotted them and then put a little circle around them. Now that's a simple way of just showing that, it's not exactly this point, that there could be some variation. And that's because it's very difficult on a graph like this to point at exactly 11.2 or 8.7. It's just too difficult to ensure our accuracy. So that gives us that visualization of error. Now, we are asked to calculate the slope of this line of best fit. So we know that that's the velocity. So if you want to write slope and do a calculation of slope, that's fine, but I just know I'm going to do a calculation of velocity, and I'm using the points on my line. Now in this, none of my points really seem to line up, but I do see that there are a couple of points. I started purposely right here on 0, 0, and I like this point right here at 8:15. Now the reason I like that is just because they seem to be pretty close to a consistent line. So I'm going to use those to calculate the slope. If you use something different, that's okay, as long as the number comes out within a reasonable amount. So let's do this calculation here. So our velocity is our position final minus position initial. So we've got 8 meters minus 0 meters. And that's from our 2 points here. And 15 seconds minus 0 seconds. Plug that into our calculator, and we will get 0.53 meters per second. So that's going to be our velocity. Now I've got that down to 2 sig figs. Now our calculation, I've written it only has 1 in 8 meters. Now from our data, it would be equally reasonable to assume that we're using, instead of just 8, that our number is indeed 8.0, because all of our positions are accurate to 1 decimal place, so you can add that decimal place to the number you read off the graph. So we've got 8.0, that's 2 sig figs, and over 15, so we're going to end up with 2 sig figs in our final answer. Now, there's 5 problems for about position time graphs. So there's this one, and just in the next couple of pages it goes through problem 2, problem 3, 4, and 5. Each of these we'll spend some time in class going over, but take some time to go through at least 1 or 2 of them before class.